This is a lecture about chemical bonding, and this particular lecture is going to focus on the Lewis electron dot approach to bonding in primarily ionic compounds. So the Lewis bonding theory uses valence electrons to explain bonding. We do know that it is the valence electrons that create chemical bonds. And Lewis structures, also known as electron dot structures, show the valence electrons around the elemental symbol. And so, for example, oxygen is in group 6A. It has 6 valence electrons, and those 6 valence electrons are shown as dots around the element symbol oxygen. So just to kind of give you a look at the Lewis dot structures for various elements, as you already know, elements that are in the same group have the same number of valence electrons. And convention with Lewis dot structures is typically to put one dot on each of the 4 sides of the element symbol before you start pairing any of them up. You will see it different ways occasionally, but this way is most common. Lewis dot structures are really handy for showing electron flow during a chemical reaction. So as I said, this PowerPoint is going to focus on ionic compounds. So let's look at the formation of sodium chloride, table salt. That being an ionic compound, a metal and a nonmetal, we know that metals tend to give away valence electrons to become cations, and nonmetals, such as chlorine, tend to accept extra electrons to become anions. And so how you would show this process with Lewis dot structures is you write the Lewis dot structure of the neutral atoms. You use an electron to show movement, you use an arrow to show movement of electrons from the sodium, which is donating its valence electron, to the chlorine. Now, all chemical reactions share a driving force that atoms are trying to get an octet of outer electrons. And so by sodium giving away its 1 valence electron, it now has, we don't show it like this, but it now has a full valence shell underneath that outer energy level that is now gone. And chlorine, by accepting an electron from sodium, also has a full octet. So just to kind of emphasize and to remind you what charge of ions the various elements tend to get, all atoms, when they bond, I like to call them noble gas wannabes. It's usually stabilizing for them to either give away electrons, accept electrons, or share electrons so that they have 8 valence electrons, okay, which we call an octet. And that gives them a noble gas-like electron configuration. So check this out. Lithium is in group 1A. So all of group 1A has 1 valence electron. And so when undergoing chemical reaction, lithium will tend to give up its 1 valence electron to become a +1 charged cation. And in doing so, it has the same number of electrons now as an ion as helium, which is a noble gas. Looking at group 2, for example, beryllium, all of group 2 have 2 valence electrons. So these elements will tend to give up 2 electrons to get a +2 charge. And by doing so, beryllium, for example, then also has an electron configuration identical to that of the noble gas helium. Well, that is the case, it turns out, for all of the A group or representative elements. They all have predictable ionic charges based on the group they're in, and by becoming ions, they all end up having electron configurations identical to the nearest noble gas. There are some exceptions to the Octet Rule, which I want you to be aware of, because when we start getting into chemical reactions, although the majority of elements are striving for 8 valence, there are some key exceptions that you just need to commit to memory. One of them is there are some elements that can accommodate more than 8 electrons around them. We call that an expanded octet. And it turns out that the larger elements are able to do that. Specifically, if the element is in period 3 through 7, it is capable of expanding its octet. So if this is the periodic table, and here's period 3, okay, so all the elements in period 3 and all the way down to the bottom of the periodic table can all expand the octet. So here's just some common examples that let you know what it looks like. And here, phosphorus has 10 valence electrons. Here, sulfur has 12. And here, xenon has 10. All right, some other exceptions to the Octet Rule going the other direction, like less than 8 valence electrons. Probably the two most common are beryllium and boron. So beryllium, believe it or not, tends to end up with only a total of 4 valence electrons, which is kind of shocking. And boron is typically very stable with only 6 valence electrons. So again, you just need to commit that to memory. All right, so let's look a little bit more at using Lewis structures to show the mechanism or the details of how a chemical reaction happens. Let's start with neutral calcium, the element, and chlorine. And always start, if you're asked to show it with Lewis dot structures, always start by drawing the unreacted, the neutral unreacted elements to begin with. And so chlorine is in group 7A and has 7 valence electrons, right? And calcium is in group 2A, so it has 2 valence. All right, so remember that both of these, as most atoms, want to end up with an octet. So we know since calcium's in group 2, it will tend to lose the 2 valence electrons to become positively 2 charged. Chlorine being in group 7A, the elements in 7A, when they chemically react, tend to get a charge of -1 because they accept an extra electron if they can find one. And so here's chlorine when it becomes an ion. Now, one thing you may not realize, when 2 elements or ions or whatever come together to bond, the overall charge must be 0, okay? All compounds overall are neutral, okay? So whatever our positive charge is, our negative charge must be equal, so that overall the charge is 0. And so since calcium's +2, chlorine's only -1, we need 2 chlorines in order to counterbalance the +2. And so what we're going to end up with is this, calcium chloride. So the subscripts that you see in chemical formula tell us how many of that atom there are in the compound. And because we had a +2, we needed 2 chlorine -1s. Then if you just add all the charges together, make sure they add up to give you 0. All right, so why don't you go ahead and give this one a try. I would put my lecture on pause and see if you can come up with the formula that you get when sodium and oxygen chemically react. I've reminded you right here of the charges they get. Now sodium's in group 1A, so the charges those elements get are +1. Oxygen is in group 6A, and the charges those elements get when they chemically react is -2. The correct answer is Na2O. Okay, so oxygen has a -2, so in order for the overall compound to be neutral, we need the positive charge to also be +2. So we need 2 sodium atoms, which is what that subscript stands for. So at the end, just make sure you add together all of the charges, and hopefully they'll all come out to be 0. Alrighty, so one other term that you need to be quite comfortable with, we're getting ready to learn how to name ionic compounds. So I want you to know what a polyatomic is. I think you probably know that poly means many, more than one. And so polyatomic ions that we've dealt with so far are just a single atom that has changed the number of electrons. Polyatomic ions are made up of more than one type of atom. So what I'm squaring right now are common polyatomic ions. They are still ions. An ion is just a charged species. It's just that they have multiple atoms that make up the ions. All right, so I kind of showed you the step-by-step thought process for coming up with a chemical formula for an ionic compound. I'm going to give you a shortcut that you may have learned in high school, which might be useful for you on a test, and that's the drop and swap or crisscross method. So as you can see here, if I asked you to write the formula for lithium oxide, it's probably intuitive to quite a bit of you that it's going to be Li2O. But a way to kind of do it quickly, especially if it's not intuitive, is you take the charge on one of the ions, and that charge, the magnitude of the charge, becomes a subscript on the other ion. Likewise, this -2 charge on oxygen, I want you to now take that 2, not the minus sign, just the 2, down as a subscript on the lithium. So you end up with Li2O1. And of course, anytime we have a number 1, we can leave it off. It's understood. I thought that was the eraser. There we go. All right, so the swap and drop is a method that, if you're in a hurry, can be good. One of the things I want to warn you with if you're using that method is the resulting formula that you get. If it can be mathematically simplified, you must do so. So you can see here Pb2O4, which is the answer you get from swapping and dropping, can be simplified further to PbO2. And if you select Pb2O4 and forget to simplify it, you will get it wrong. So it's very important to simplify if you can after you crisscross. Here's a summary of the key points if you are trying to write a formula for an ionic compound. So again, ionic compounds are made up of cations and anions. So you have to, it's critical that you show the charge on both of those. The sum of the charges of the cations and anions must add up to equal 0 so that the compound overall is neutral. And finally, the formula for an ionic compound is an empirical formula, meaning it's the most simplified formula, okay? Smallest whole number ratio of ions. All right, so we've talked about writing the formula for ionic compounds, and now we're going to talk about how you go about naming the compounds if you're given the formula. So there are 2 broad categories of ionic compounds as far as naming rules. Both of, or all types of ionic compounds will name the cation first. So the cation comes from the metal, and that name is simply the name of the element. Very, very easy. We'll do a bunch of examples. And what's named second in an ionic compound is the anion, which came from the nonmetal. The 2 different types of categories are if the metal is one of the group A metals versus a transition metal. So if it's a metal from group 1A, 2A, etc., that's much easier and straightforward to name than if there's a transition metal, which it gets a lot more complicated. All right, let's talk about the easy ones first. So a binary compound, that's one that has, like sodium chloride, NaCl, okay? Binary means only two different types of elements. So that would be as opposed to, let's look at this, okay? If you have something like this, that is not binary because you have sodium, sulfur, and oxygen. You have three different elements, so that is not binary. So if we have simple binary ionic compounds, as I said before, always start by naming the metal first, potassium in this case, okay? And then name the anion or the nonmetal last, but change the ending of it to the suffix IDE. So this is potassium, same name as the element, and then chloride. And CaO is calcium oxide. So pretty simple. All right, so now we'll go on to the little bit more challenging type of ionic compounds to name. And those are ionic compounds that contain a transition metal. That's what they mean by type 2. So if you have a transition metal, you do not necessarily, well, you don't know the charge on the metal when it undergoes chemical reaction. And that's because most transition metals, almost all of them, have variable charge. So for example, sometimes iron, when it chemically reacts, has a charge of +2, and sometimes it has a charge of +3. That's true for almost all the transition metals. So as a chemist or a reader, if you look at the formula for an ionic compound, how do you know what charge, in this case, that the copper has, if it can have more than one? Well, it's going to involve some simple math, but what I want you to understand at this point is whatever the charge is on the transition metal must be shown in the name using Roman numerals, right? So copper 1 oxide is the name of this. How did I know that? How do I know that copper has a charge of +1? All right, so this is what I do. You have 2 coppers, right? So I'm going to go ahead and draw out 2 coppers and 1 oxygen. Now, copper's a transition metal. I don't know yet what charge it has in this compound, but I do know the charge of oxygen. It's in group 6A, and they have a common ion charge of -2. I also know that ionic compounds overall must be neutral. So the only way that can happen is if each of the copper ions has a +1 charge, because +1 + 1 - 2 is 0. And so in this case, copper has a +1 charge. Similarly, CuO, I know oxygen is -2. There's only 1 copper, so its charge has to be +2 in this particular compound. There are 2 metals that are not transition metals, but that behave like transition metals. They have variable charges, and when compounds containing lead or tin, you must include Roman numerals in the name, just like you do for the transition metals. So you just need to commit these to memory, that lead and tin act like transition metals and require the use of these Roman numerals. So just as a reminder to make sure it absorbed, whatever the charge is on the metal cation, if it's a transition metal, is shown in Roman numerals while you're naming it, okay? All right, so let's try an example. CrBr3. So you want to get into the habit of anytime you're naming something, your first question should be, is the metal a transition metal? Okay, so you've got to have your periodic table out. It turns out that chromium is in fact a transition metal. So I know my name is going to get a little bit complicated. So the beginning of it is certainly chromium. You may be able to intuitively determine that it's chromium +3, but if not, I'm going to show you how. So you have 3 bromines, bromines in group 7A, so I know the common ion charge those elements have are -1. And then I only have 1 chromium, but this overall compound has to be numeral. It has to be equal to 0. So my total negative charge is -3. So my total positive charge has to be +3, which means chromium has a +3 charge. So that's where the Roman numeral 3 is coming from in the name. And just like binary ionic compounds, the final non-metal name ends in IDE. One last thing to point out. I mentioned polyatomic ions earlier, for example, just to give you a look of some of them. And so they will commonly be part of an ionic compound. So I could have something like, let's see, carbonate. I could have something like magnesium carbonate. And so you're going to have to name those too. But the polyatomic ions, there are several of them that you'll just have to memorize because I won't give you a table on the test. And I will list those out later for you. Because you need to know their name, commit their names to be able to write names for compounds. So, for example, let's say I asked you to write the name for NaNO2. All right. So remember, always write the name of the cation first, and that's sodium. It's given its full element name. So the name is going to start with sodium. And then you have to be able to identify this NO2 as a polyatomic. Okay, so that's really important because I always end up with some students that try to name this glob as like individual atoms. They'll say like, well, sodium dioxo, no. So as soon as you identify you have a polyatomic instead of a binary, you need to know the name of that. And so it happens to be nitrite. Okay, so again, that's just committing to memory. And here's a list of common polyatomic ions. And the ones that are most commonly used that you should try to commit to memory: acetate, carbonate, I prefer to call this bicarbonate, hydroxide, nitrate, chromate, dichromate, phosphate. Let's see, I think that might be it. Oh, here we go. We'll get the 2 sulfurs, sulfite. All right, so here's an example for you. And I got the answer here, so you can't really put the video on pause, can you? All right, so you can always pretty much spit out the name of the metal, lithium. Now, this is polyatomic, so you need to look it up, and you'd find that it's called the dichromate ion. Alrighty, and that's it. Lithium dichromate. Now, lithium is not a transition metal, so you don't need the Roman numerals. You just leave it like this, lithium dichromate.